Hi friends, in power electronic circuits we have already studied phase control rectifier, that is AC to DC converter. Then we studied chopper circuits, that is DC to DC converter. Now we will study inverter, that is DC to AC converter. In case of inverter, in the input we will have DC source and the output we will expect AC voltage. This converter will be called inverter. Okay. Before this we have studied phase control rectifier, where input is AC and output is controlled DC. And in case of chopper circuits, input is DC and output is controlled DC. Apart from these converters, there is one more type of converter where input will be AC and output will be controlled AC. So inverter are basically of two types. First we will have voltage source inverter, in which the input will be a DC voltage source, and second is current source inverter. There a current source will be input for this. In current source inverter we will have a current source as DC input. So let us start with single phase full bridge voltage source inverter. First of all, we will have a DC voltage source, and we will have a switch here, and here between these two terminals we will have load. So let us first start with the most basic load, pure resistive load. These four switches are control switch. These will conduct in the downward direction if the gate signal is applied. Okay, and here you have a DC voltage source. This will be the reference for output voltage. Let's say this is switch 1, this is switch 2, this is switch 3, and this is switch 4. Okay, so first we will find out the tendency of current flow. This is a DC voltage source, so the tendency of current will be to flow in this direction. Now if S1 and S4 will conduct, this current will flow through this short circuit, and this current will be very high, so we will try to avoid simultaneous switching of S1 and S4. Similarly, if S3 and S2 are simultaneously given gate signal, this will also provide a shorted path, so in this case also current will be very high. When S1 and S2 is given signal simultaneously, then current may take this direction, this path, from left to right, then through switch S1, then through load, then switch S2, and it will come back to negative polarity of voltage source. I am drawing diagram showing switch only. Here you have resistive load. This is S1, this is S2, S3, S4. So when S1 and S2 will be conducting, these two switches will be connected. Here you have positive reference, here you have negative reference. Now if you will apply KVL here, here you will get gain of VDC, here you will get drop output voltage, and this way loop is completed. So V0 will be VDC. Okay. So S1 and S2, if these two switches are conducting, you are getting positive voltage. So I will name these two switches as positive leg. Okay. When these two switches are open circuited, and let us say S3 and S4 are conducting. If S3 and S4 will conduct, what will happen? Now if you will apply KVL, here you will have gain of VDC, here you will have gain of, you are moving in this direction, here you have gain of V0, and loop is completed. In this case you will get V0 equal to minus of VDC. So the leg S3 S4 will be called, I will name it as negative leg. So if positive leg is conducting, you will get positive voltage. Corresponding to negative leg, the voltage will be negative of this DC voltage source. So let us draw the output voltage waveform for this circuit. Let's say at t equal to 0, S1 and S2, these two switches are given signal simultaneously. The gate of switch S1 and S2 can be connected with the same signal. Okay, so both switches will be turned on at the same time. Let's say initially you have given signal to, let's say this is for S1 and S2, and this graph is for signal of S3 and S4. So when S1 and S2 are given gate signal, S3 and S4 must be turned off, because if S1 is conducting and at the same time if S4 is given signal, this will make a short path, so that will be dangerous. So when S1 S2 are conducting, S3 S4 must not conduct, this must not be given gate signal. Okay, in this case what will be the output voltage? If S1 S2 will conduct, output voltage will be plus VDC. Okay, and let's say at this instant switch S1 and S2 are commutated, means switch S1 and S2, this gate signal of S1 and S2 are removed, these switch S1 and S2 are turned off, and after some time S3 and S4 are given signal. Okay, so after this point you will get negative voltage. Okay, then again S1 and S2 are given signal, so here you will get positive voltage. This is positive VDC, this is negative VDC. So in the output you are getting, although you are getting a square wave, but it has opposite polarity. Okay. So in an inverter, what we are doing, we have given a DC voltage source as input, and alternate way we are giving signal to switch S1 S2 and then switch S3 S4. So corresponding to S1 S2 you will get positive voltage, and S3 S4 we are getting negative voltage. So this way we are getting a voltage waveform of opposite polarity. Next, if we change the load as, okay, here we have resistance only. Now let us draw graph for current, output current. The reference of output current we will take it as from positive reference to negative reference. So since the load is resistive, the waveform of I naught, what will be the I naught? I naught is V naught divided by R. Okay, you are just dividing voltage by a constant, so the characteristic of I naught and V naught will be same. So when V naught is positive, current I naught will be positive and magnitude will be V naught by R. When voltage is 0, current will be 0. Through resistance, current can be made suddenly 0, but if at the place of resistance, if we had inductor here, current could not go to suddenly 0. Next, here we are getting negative voltage, so the current will be negative, and the magnitude will be V naught by R. So drawing waveform of current is very easy because in the load we have connected a resistance. Now for the next case, let us connect an RL load here. In the load, I am connecting an RL circuit, RL load, and output voltage will be taken across the whole RL load, not across resistance. Since the load is RL load, so output will be taken across the load only. This is output voltage and this is output current. Here we have S1, S2, S3 and S4. Let us assume the same switching sequence. Here we'll have graph of V naught and here graph of I naught. Okay. So to start, let us consider switch S1 and S2 is connected. Okay. If these switches are conducting, what will happen? The output voltage will be, if you move in this loop, the output voltage will be certainly VDC. Okay. From here you will get output voltage as VDC. So the same voltage will be applied across RL load. Across RL load, you will have a voltage of VDC. So the inductor current, what will happen to inductor current? Inductor current will start from 0. If you are starting this circuit from rest, inductor current will start from 0 and it will start rising. The graph of inductor current will be like this. This will be given by this formula, IL equal to V divided by R into 1 minus e to power minus t divided by tau, where tau equal to L by R. This equation we have already studied in the lecture of network, in the lecture of first order system. And let's say at this point when S1 and S2 was disconnected. Now at this point, up to this point, the inductor current, the inductor would have gained some significant amount of current. Although in steady state this current will not start from 0, but since we have started analyzing this circuit from rest only, so I have taken the initial value of inductor current as 0. But in a steady state, the inductor current, we cannot start from 0. Okay, so at this point inductor has gained a significant amount of current, and let's say here S1 and S2 are disconnected. So if S1 and S2 are disconnected, these switches are opened, okay, and S3 and S4, these are connected after some time. Why I have maintained a gap here? Because to avoid the overlapping, let's say when S1 and S4 will be connected simultaneously, you will have a short circuit. So to avoid the short circuit, I have maintained a gap between switching of S1, S2 and S3, S4. Now in this gap, what will happen? Consider this region only. In this region, neither of S1, S2 nor S3, S4 are conducting. So all the switches are open, but at this point inductor has gained some amount of current. So, and you know that inductor current cannot be made instantaneously zero, so you have to give some path to the inductor current. To this inductor current we are required to give some path. Okay, I hope you understood it. Initially S1 and S2 was connected, so current through inductor started rising. Up to this point inductor has gained a significant amount of current, and at this point S1 and S2 was disconnected and S3, S4 are not conducting. Neither of S1, S2 nor S3, S4 are conducting in this interval. So there is no path for inductor current, but inductor current cannot be made zero instantaneously. Okay, so you need to have a path for inductor current, and to provide that path we connect anti-parallel diode through switch. First I am connecting anti-parallel diodes, and later we will see how this diode will serve the purpose of flow of the inductor current. So this is D1, this is D3, and remember switch will conduct in downward direction. Okay, now if we have diode in this fashion, now what will happen at this point? Inductor current has to flow in from left to right. Okay, if I take the reference I0, so this direction will be called positive direction of current and this direction will be negative. So if I say the current is positive, you will understand that current will be flowing from left to right. So we have a positive amount of current here. Now if S1 and S2 is disconnected, between this interval what will happen? This current will flow through, this has to flow in right direction, so here current will be positive. Now the current may go in upward direction as well as in downward direction. In the downward direction S2 has been disconnected in this interval, S2 is not conducting and diode cannot support this direction of current, diode will be reverse bias, so current cannot go in the downward direction. So whatever current is positive here, all this current will be in upward direction. In upward direction, in this interval, no switch is conducting, means none of the main switches are conducting. This is open, but to this direction of current, diode can conduct. Okay, so here diode will be, this current will flow through diode 3. Okay, here only one path. Now, can this current may come in downward direction? In the downward direction, S1 is not conducting and D1 will not support. So this current will go through source and it will enter in the positive terminal of source, it means this source will absorb energy. Okay, if a current is entering into positive terminal of any source or any element, that element will absorb energy. In this case it is absorbing energy. And who is providing energy? This inductor will be providing energy. The stored energy in the inductor will be dissipated in the resistance R, as well as some part of this energy will be absorbed in the source. Okay, so after this point current will flow through here. Okay, now current will come in this direction. Okay, and whatever current is flowing from here, it has to come from this direction only. So this current will flow from, this will go in upward direction. So S4 is not conducting, so this will flow through D4. Okay, this will be the direction of current through anti-parallel diodes. So whenever S1, S2, these switches are disconnected, or we did force commutation of S1 and S2, the inductor current will take path of anti-parallel diode D3 and D4. The right direction, the positive direction of inductor current will take path of D3 and D4. And whenever D3 and D4 are conducting, what will be the output voltage? D3 and D4, these are connected in negative leg. So here we have negative leg is conducting. Either S3, S4 conducts. In this situation, we will say negative leg is conducting, or at the place of S3, S4, if D3, D4 are conducting, we have again the same thing, the negative leg is conducting. So when negative leg is conducting, the output voltage will be minus VDC. So here what will you get? In this region the output voltage will be minus VDC. So right after this point you will get minus of VDC. Up to this point current will rise to some value, and after this what will happen to current? Here you are getting minus of VDC. Let's say this is output. You have this type of circuit RL. This is positive reference, this is negative reference. Okay, so you can take positive here, negative here, and what is voltage? The output voltage. So here this is the output voltage, and what is I naught? This is the positive direction of I naught. Okay, but what happened after let's say this is instant 1. What happened after instant 1? The polarity after instant 1, output voltage is minus VDC. Initially output voltage was plus VDC, so initially this voltage was plus VDC, and after point 1 what happened? V naught has changed its polarity. So in the next case output voltage will be, this is polarity of output voltage, and current is in right direction. This current is flowing through diodes. Now what will happen? Since this current is flowing due to the stored energy of inductor, okay, so inductor energy will be dissipated both in resistance and in the source. The current will enter into the positive terminal of source. So this current will decay very rapidly, and the formula for the inductor current will be, this current will be, can be found out with the help of this formula. ILT will be I infinity minus I infinity minus I naught into e to power minus t divided by 2. But instead of using formula, calculating exact equation of current is not important. I just want to show you that the stored energy of inductor is being dissipated in source as well as in resistance. So the stored energy of inductor will half Li square will decay very rapidly. And how it will decay? How this energy will decay? When the magnitude of current will decrease. So after this point we will say the magnitude of inductor current will decrease rapidly. This will be the graph. So at this point the inductor current will be 0. Now let us analyze this interval. In this interval the current is flowing through diodes D3 and D4. What you have to do, after when the switch S1 and S2 are disconnected, at this point, let's say this is instant 2, at instant 2 you have given gate signal to S3 and S4. Okay, you are trying to turn this switch on. Okay, this is instant 2. Okay, and this instant is 3. At instant 2 current is still non-zero and it is flowing through switch D3 and D4. Whenever current will flow through D3, every switch has its on state voltage drop. If current is flowing in upward direction, it will have some on state resistance, and due to this resistance there will be a voltage drop. Okay, so this will have a voltage drop according to this polarity. Here you have positive and here you have negative. Okay, you have, let's say you have a thyristor here. So what will be the polarity of thyristor? Thyristor will be connected like this. Okay, and what is the polarity of voltage? This is polarity. And where this voltage comes from? This is the on state voltage of diode. So due to as long as current is flowing through this diode, there will be on state voltage drop, and due to that voltage drop, this switch S3 will be reversed bias. And if the switch is reversed bias, it does not matter whether you are giving gate signal to this switch or not. The switch will be in off state. So as long as current is flowing through D3, current is flowing up to 0.3. So up from 0.1 to 0.3, even if you will give a gate signal to switch S3, the switch S3 cannot be turned on because it is reverse biased. It is reverse biased due to on state voltage drop of D3, and similar argument can be made for switch S4, because if current is flowing through D3, obviously it will go through D4, and due to on state voltage drop of diode D4, the switch S4 will be reverse biased. So at instant 2, even if you are giving gate signal to switch S3 and S4, at instant 2 this switch cannot be turned on. This switch can be turned on only after the current through diode D3 and D4 has decayed to 0. But in the output you will be getting negative of VDC, because the negative leg is conducting through D3 and D4. Okay. Now what will happen after this point? This is point 3. The current through diode has decayed to 0. So now current is not flowing through this diode. Okay. If current is not flowing through this diode, now there is no more voltage drop across diode, and switch S3 and S4 will not be reversed wise. Now if these switches are not reversed wise due to this tendency of current, these switches will come in forward mode, and by giving gate signal these may be turned on. So after this point, after point 3, switch S3 and S4 will start conducting. Let's say this is switching of S1 and S2, and this is switching of S3 and S4. This is S1, S2, and this is S3, S4. Here you have waveform for output voltage V0, and here you have waveform for output current I0. So when S1 and S2 are conducting, or let us assume that initially you are getting positive output voltage. Let's say this is instant 1, this is instant 2. Let's say you are getting positive voltage here. So corresponding to positive VDC, current will increase in positive direction. So let's say current has risen to this value, and at this point S1 and S2 are commutated. Okay, when S1 and S2 are commutated, when S1 and S2 were conducting, current has increased in positive direction. Okay, and when these two switches are commutated, this current, the positive direction current, is now flowing through D3 D4, and if D3 D4 will conduct, means negative leg is conducting, the output voltage will be negative of VDC. So immediately after turning off S1 and S2, diode D3 D4 will conduct, and if diode D3 D4 will conduct, you will get negative voltage. Okay, and if you will get negative voltage, here I have reversed the polarity, the output current will decay rapidly. The output current will, because this source, the tendency of this source is to flow the current in anti-clockwise direction, but initial current is in clockwise direction. So first this clockwise current will decay to 0, then current in anti-clockwise direction will rise. So first the clockwise current is going to 0, and then current in anti-clockwise direction will rise. During interval 1 and 2, no switch is given gate signal. That's why no main switch will be conducting. Between interval 1 and 2, diode will be conducting. After point 2, switch S3 and S4 was given gate signal, but S3 and S4 was reverse wise due to on state voltage drop of D3. So even after point 2, even after instant 2, switch S3 and S4 will not conduct. Okay, at instant 3, the diode current has decayed to 0, so there is no more on state voltage drop. So after point 3, gate signal is continuously applied. So after point 3, S3 and S4 will start conducting, and does not matter whether D3 and D4 are conducting or S3 and S4 are conducting, the output voltage will be negative of VDC. Between this interval, D3 and D4 are conducting. Okay, and after this instant, S3 and S4 are conducting. Now let us, this instant is 4. Okay. At instant 3, the clockwise current decayed to 0, and after this anti-clockwise current started rising. So clockwise current is here, this direction of current is taken positive. So anti-clockwise means right to left direction of current will be negative. So current in anti-clockwise direction rises means the negative value of current is rising. Let's say this current will rise up to this value. At instant 4, let's say S3 and S4, at this instant, this is instant 4, S3 and S4 are disconnected. Okay, these are commutated. Now what will happen? Naming will be, this is 1, either switch 1 or D1. This is 2, this is 3, and this is 4. Okay, so we were talking about this instant. At this instant, current is negative, means current is flowing right to left. Okay, we are talking about instant 4. Current has some value in this direction, and at this instant, S3 and S4 are commutated, means these two switches are not conducting. Okay. At instant 4, S3 and S4 are commutated, and let's say after some gap, some interval, S1 and S4 are again given, S1 and S2 are again given gate signal. Okay, let's say this instant is 5. So what will happen between instant 4 to 5? Between instant 4 to 5, after 4, S3, S4 was disconnected, and S1, S2 are given signal at instant 5. So between 4 to 5, none of the main switches are conducting. Okay, but at instant 4, all the main switches are disconnected. But at instant 4, inductor has some amount of current which is flowing from right to left. So between instant 4 to 5, before instant 4, if we talk about what was the path of current, the current was flowing in this instant, S3, S4 are conducting. So current was flowing in this path through source, then switch S3, then this direction, then switch S4. But S3 and S4 are now disconnected, and inductor current has to flow in this direction. So now what will be the path to this direction of current? This switch is disconnected and diode will not support. This current will go in upward direction. Okay, switch S1 is disconnected, so the current will take the path of diode 1. If current is flowing in this direction, it has to come from this. Now this current cannot come from the upward direction because this switch is disconnected. This is S3, and diode cannot support this direction of current. So this direction has to come from downward direction. Main switch is not conducting, so this will come through diode D2. Okay, this will be the direction of current. Okay, again start analyzing from here. This current is going in upward direction, then the source. Okay, and this way it will complete the closed path, right to left, then diode D1, then source, then diode D2. So this way it will close the path. Now when diode and D1 and D2 are conducting, it means positive leg are conducting, and if positive leg is conducting, what will be output voltage? Output voltage will be again positive. This is the positive output voltage. Okay, so again you have this voltage, and at this instant, what is the direction of current? The direction of current is right to left. The direction of current is right to left, and this is the polarity of output voltage. Now again, what happened in this case? Output voltage is positive, but again current is entering into the positive terminal of voltage source. So the stored energy of inductor is being dissipated in the resistance as well as in the DC source. So again this magnitude of this current will rise rapidly. Talking about instant 5, just before instant 5, no main switch was given gate signal. S3 and S4 were commutated and S1 and S2 was not given signal. But right after instant 5, S1 and S2 are given signal, but current is flowing through D1 and D2. Okay. At instant 5 also, current is still flowing through D1, D2. So there will be on state voltage drop of D1, and on state voltage drop of D1 will prevent the switch S1 from turning on. Similarly, the on state voltage drop of diode D2 will prevent the switch S2 from being turned on. So even at the instant 5, you have given signal to switch S1 and S2. At this instant, switch S1 and S2 will not turn on. Instead, it will wait for the negative direction of current to fall 0. At this instant, the negative direction of current falls to 0 because the DC source has tendency to flow the current in right to left direction, left to right direction. So first the opposite direction of current will decay to 0, and then it will again start rising in the direction where the voltage source wants to drive the current. So what we discussed, even after 0.5, switch S1 and S2 will not be turned on because it will be reversed bias due to on state voltage drop of D1 and D2 respectively. At this point, the current decays to 0. So after this point, switch S1 and S2 will be turned on. Okay. Let's say this instant is 6. So between 4 to 6, which switches are conducting? Between 4 to 6 diode D1 and D2 are conducting, and does not matter whether D1 and D2 are connecting or switch S1 and S2 are connecting. In both the cases, the positive leg will conduct. Okay. In both the cases, positive leg will conduct, and if positive leg conducts, output voltage will be positive VTC. So if D1 and D2 are conducting, output voltage will be positive VTC. Okay. And after 6, S1 and S2 will be turned on, so again you will get positive voltage. And since current is 0, now the opposite direction of current has decayed to 0. So now current will start rising in positive direction. So now current will rise. Now you can observe that whenever diodes are conducting, the output voltage and the current has opposite sign. When D3 and D4 are conducting, what is the output voltage? D3, D4 are connected in negative leg, so obviously output voltage will be negative. The output voltage is minus VDC. And why D3, D4 are conducting? Because before D3 and D4, the direction of current was positive, and switch S1 and S2 were before conduction of D3 and D4. Switch S1 and S4 were conducting, and inductor has a current, significant amount of current in the positive direction, and you disconnected switch S1 and S2, so current has to be positive. So this positive current, you need to give a path to this positive current. So this positive current will flow through D3 and D4. So whenever D3 D4 will conduct, obviously it will conduct in upward direction. D3 will conduct in upward direction, so it can support only this direction of current. D4 will conduct in this direction, so it will support left to right direction of current. Okay, and what is left to right direction of current? This is a positive current. So D3 D4 will support positive current, and whenever D3 D4 will conduct, output voltage is negative. Okay, so voltage is negative but current is positive. So whenever D3 D4 are conducting, voltage and currents are in opposite sign. Similarly for D1 and D2, D1 will support current in upward direction, D2 will support current in upward direction. So D1 and D2 will support the current of negative current. Okay, this is positive reference, negative reference voltage. And whenever D1 D2 conducts, positive leg conducts, it means voltage will be positive. So for D1 D2, voltage is positive, V is positive, and I is negative. Okay, and for D3 D4, voltage is negative and current is positive. Since in case of diode, voltage is always opposite to current. Okay, if voltage is opposite to current, the magnitude of current will decay. Whenever D3 D4 conducts, the positive magnitude of current decays, and in case of D1 D2, the negative magnitude of current decays towards 0. Okay, whenever main switches will conduct, when S1 and S4 are conducting, when S1 and S2 are conducting, or when main switches start conducting, the main switches start conducting only at the point when diode current falls to 0. Okay, so we can say that the main switches start conducting when the current is 0, or whenever main switch starts conducting, the current will start from 0. So when switch S1 and S2 are conducting, the voltage is obviously positively conducting. So voltage will be, for S1 S2, voltage is positive, and at the start of conduction of switch S1 and S2, initially current was 0. So if you will give positive voltage, the current will start rising in positive direction. So for S1 S2, current will be positive. Similarly for switch S3 S4, when S3 S4 will start conducting, obviously current will start from 0. So when these switches conduct, voltage is negative, and in the beginning current will be 0. So negative voltage will drive the current in negative direction. So current will also be negative. So whenever switches conduct, the polarity of output voltage and current will be same. For S1 S2, voltage is positive, current is also positive, same sign. For S3 and S4, voltage is negative, current is also negative, same sign. And for the diodes, you can easily find out the polarity of voltage by checking whether the diode is in positive leg or negative leg, and current will be always of opposite of sign of voltage. You can also observe from graph. Here D3 D4 are conducting, and here S1 and S4 are conducting. So when S1 S4 are conducting, voltage is positive and current is also positive. Although in steady state this current will not start from 0. This current will start like this. So please observe in the third half cycle, whenever output voltage starts becoming positive, before switches S1 and S2, D1 and D2 conducts. So let's say at this point the output voltage starts becoming positive. So first D1 D2 will conduct. In this interval D1 D2 will conduct. In the start of either positive cycle or negative cycle, first diode pair will conduct, and when the current through diode pair will decay to 0, then switches will start conducting. Okay, now we have these informations: sign of voltage and current corresponding to conduction of different switches and diodes. So with the help of this information, now let us try to again draw the graph with the help of this information only. We will not do the detailed analysis, we will just draw the graph with this information. Now first I will draw the graph of output voltage, and I will draw the graph of output voltage V plus VDC and minus VDC. Okay, the duration for which the output voltage will be positive VDC, for the same duration the output voltage will be negative VDC, because the switching sequence is symmetrical. Both the switches of both the legs are being turned on and turned off for the same duration. So we have a symmetry in the positive sequence, in the switching sequence. So for equal intervals you will get positive and negative voltages. This is nothing but graph of output voltage. Here you have output voltage, and you are applying this output voltage to an RL load. Positive, negative, this is positive, here you have negative, and you have a source here. The output voltage V0 will act as a voltage source for the RL load. And how is this voltage source? This voltage source is a square wave. Okay, so now we'll try to find out this current I0 in a steady state, not with the help of circuit. We have a voltage source, we have a waveform of voltage source, and we are given with this circuit. So let us try to find out current here with the help of this waveform. We will say V0 is nothing but, if you will apply KVL, let's say here the voltage drop is VR and here voltage drop is VL. You will write V0 equal to VR plus VL. V0 will be equal to, I'm trying to find out the average value of inductor current. V0 is nothing but I0 into R plus L d I0 by dt. And since the input voltage is How is the nature of input voltage? This is a square wave and this is periodic. So if input voltage is periodic, every quantity in the circuit will be periodic. If you connect a periodic waveform, this we have also studied in the lecture of in phase control rectifier. We studied this concept. In the chopper circuit also we studied this concept. If the input voltage is periodic, if you have RL load, so voltage across resistance, voltage across inductor, this current, everything will be periodic. Let us write it as VL only. So we will say inductor current IL is periodic. Okay, and what we have studied in phase control rectifier and in chopper circuit, we have studied flux balance. And what flux balance says, if inductor current is, if IL is periodic, then average inductor voltage, the average value of inductor voltage will be 0. Okay, I will not prove it here because I have already proved while discussing phase control rectifier and chopper circuit. There I have already proved this concept, why average inductor voltage is 0 if inductor current is periodic. So I'm just going to use it here. Since input voltage is periodic, so everything in the circuit will be periodic, hence IL will be periodic. And if IL is periodic, the average value of, not instantaneous value of inductor voltage, but the average value of inductor voltage will be 0. Now you have V naught equal to, if you will apply KVL here, V naught equal to I naught R plus VL. So apply average both sides. So V naught average will be I naught average into R, because R is constant, so average will go to I naught plus VL average. And with the help of flux balance, average inductor voltage is 0. So this quantity is 0. What is average value of output voltage? You are getting positive and negative voltage for the same duration. So this voltage is also 0. Now if you will calculate average value of I naught, you will get average value of I naught as 0. I'm not saying the current will always be 0. If I'm saying average value of I naught is 0, it doesn't necessarily mean that I naught will always be 0. I naught may have positive value for some time, it may have negative value for some time, and area, the positive area and the negative area will be exactly equal and they will cancel out, hence you will get I naught average as 0. Okay. So now we will draw first axis for I naught. So in the graph of I naught, at least we know that the average value is 0, so the average value will be on the x-axis, the time axis only. But here you have a circuit. If you will apply a square wave, this is very easy to observe that current will not be always 0. When you will give a positive voltage, the tendency of current is to flow in clockwise direction, okay, or is to flow from left to right, and left to right direction of current is positive. So when we will say, when output voltage is positive, current will tend to be positive, okay, or we'll say current will increase. And whenever voltage is negative, current will tend to decrease. And since this is first order circuit, so if current will increase this way asymptotically, and current decreases this way. This we have studied in first order circuit in network. Okay, so now we have information about the average value of current. Okay, average value of current is 0, and this is also very easy to observe that current will not always be 0. current will have some positive value, current will have some negative value, and you have to maintain the average value constant. So you will make such a graph of current that the positive area must equals the negative area to get the average value as 0. Okay, so we have to make positive and negative area equal. Okay, and we have also we have this information that whenever voltage is positive, current will rise. So in this interval we have positive voltage, so in this interval current has to rise. Okay, so whenever a quantity starts rising, just before starting rising, at just before the rise, the quantity will be at minimum value. Okay, suppose you have this type of graph for some function. If I ask you at which point this graph starts rising, you will certainly say it seems that after this point this graph starts rising. So this is very easy to observe that this value will be minimum. Okay. Okay. So in this interval voltage is positive, in this interval current will start rising, and if it starts rising, it will start rising from minimum value. Now okay, so it will start from minimum value and it will rise up to, this is, let's say this is 0.1, it will rise up to 0.2. After 0.2 it will start decreasing. Okay, let's say you have this kind of graph. So the point, now if I ask you what is the point when this graph stops rising, so you will say at this point this graph stops rising, after this point it starts decreasing, so this will be the maximum. So at point 1 the graph will be at minimum value, and at point 2 the graph will be at maximum value, and you have to make the total area 0. So I'm first plotting it, and it has to rise this way only. In the first order circuit, inductor current rise this way. Okay, I have drawn this type of graph. In this graph I have maintained the minimum value, the negative value of current same as the positive value of current. You may observe that the negative area is not equal to positive area. It seems that the positive area is greater than negative area, but the time period has not been completed yet. You have to get overall 0 area in one time period. Okay. Similarly, after this point it will start decreasing, and it will decrease up to this point. So here you will have minimum value, and the way of decreasing is, this is the concave curve. Okay. This is complete cycle where you have positive area and this is negative area. So this will be the graph of current. Although I took much time to explain it, but once you have understood it, drawing is very easy. I did not introduce any new concept. I used flux balance. This you have already studied in phase control rectifier and chopper circuit. If you have not studied, this is available. The video lecture is available for chopper circuit and phase control rectifier. It has also been uploaded on YouTube, so you can search there. Okay, so first I have drawn a conclusion that average current will be 0, and you have to equate the positive and negative area. And with the symmetry, the negative maximum of current will be equal to positive maximum. So if you have this much information, you can draw the graph. And since this is periodic, so the same type of graph will be repeated. Now once you have waveform of output voltage and output current, now you can decide Now you can figure out in what interval which switches will be conducting. Suppose I am talking about this interval. First of all, decide whether the sign of voltage and current are same or not. Okay, the sign of voltage is positive and sign of current is negative. So voltage and currents are of opposite sign. This means a diode pair will conduct. There are two diode pairs, D1 and D1 D2 and D3 D4. Okay, since voltage is positive, so diodes of positive leg have to conduct. Since voltage is positive, so in this interval diode D1 and D2 will conduct. Let's say this is second interval. In the second interval, the voltage and the current have same sign, so main switches will conduct. Main switches are S1 S2, S1 S2 and S3 S4. Since the voltage is positive, so positive leg has to conduct, so the main switches will be S1 and S2. Here S1 S2 are conducting. Let's say this is third interval. So in the similar fashion you can figure out that in this interval T3 T4 will be conducting, and in this interval S3 S4 will be conducting. Now I'm going to draw the graph of inductor current again for the same RL circuit, same RL load in the inverter. I'm again going to draw the waveform of output current when the resistance is negligible. Either resistance is negligible or inductance is high. In both the cases, the time constant L by R of the circuit will be high. Okay, I'm going to draw the waveform of output current when the time constant of circuit, this RL circuit, that is L by R, it is much larger than this switching interval. This is the switching interval when the time constant is much greater than the switching interval of the output voltage. So whenever time constant is high, we have studied in RL circuit, if the time constant is very high, the transient decays very slowly, or if tau is high, the changes in the circuit will be relatively slow. For example, here what are you finding? In this interval, the change in current is, this is the amount by which current changes. Okay, if time constant is high, this change will reduce. For an RL circuit, let's say you have a voltage source and RL circuit is connected to this voltage source. In this voltage source, the equation of current will be V divided by R into 1 minus e to power minus t divided by tau. The graph of current will be like this. Now if you will, we have already studied it. If you will refer that lecture, you will understand it very well, but I am still trying to explain. If you will increase the value of tau, let's say this is the graph of inductor current at value of tau 1. Now if you will increase the value of tau, you will get this kind of graph. Let me try it again. Let's say this is the final value of current, V divided by R, and this is for tau 1. Now if you will increase the value of time constant, we know that if you will increase the time constant, the response of first order circuit will be slower. It will get slower. So if you will increase tau, the graph will look like, if you further increase tau, graph will look like this. The final value will go to V upon R only. I'm not saying that final value will be less than V by R, but the time taken in the later case will be highest. This will also go to V by, all the graph will reach to high V by R finally. But if you will increase the time constant, let's say this is tau 4, this is tau 3, this is tau 2, and tau 4 is greater than tau 3 is greater than tau 2 is greater than tau 1. In the lecture of RL circuit, I have shown all these things with the help of example, numerical example. So if you will increase the value of tau, the final value of current will be P upon R only, but the time taken to reach the final current will be the practical time taken to reach to the final value of current will be highest when the time constant is highest. So this was about in terms of reaching the final value of current. If you will observe the graph which is for least value of tau, it looks like curve. If you will select some region, it fairly looks like a curve. But for tau 4, if you select the same duration, in the same duration it looks like a straight line, more like a straight line. So if you will increase the tau for a given interval, the graph will look like a more like a straight line. So this is what I wanted to explain. Now we have to draw the waveform of current in inverter circuit when tau is high. So this is nothing but waveform of an inductor current in first order circuit. Now if you will increase tau, here it looks like a curve, you have to make it like a straight line. Okay, but one thing is sure, the input voltage or the output voltage of inverter is acting like the source voltage here. The average output voltage is 0. If I again write the equation, V naught equal to I naught R plus VL, you apply average value. Source voltage is periodic, so inductor current will be periodic, so average inductor voltage will be 0, average output voltage is 0. So even if you increase tau, there will be no difference to the average inductor current, which will be 0. So while making graph of inductor current in the higher value of tau, we again have to stick to the same concept that the average value of inductor current will be 0. This is first half cycle, this is second half cycle, and the graph has to look like a straight line. Okay, you have to maintain the average value 0, and so and by symmetry the minimum negative value will be equal to maximum positive value, but the variation will be small in this case because inductor current does not tend to change very much in the same interval. We are considering the same interval. For lower value of tau, the change will be this much. For higher value of tau, change will be relatively smaller, and graph will also look more like a straight line. So now you are going to get a graph which looks like a straight line. You get this kind of graph, and switching sequence will be same. Here current is negative, voltage is positive, so here you will have D1 D2. In this interval you have S1 S2. In this interval D3 D4, and in the remaining interval S3 S4.